Hello everyone, today I want to introduce my work about an analytical tractable exponential component for monitoring the alkali-aggregate reaction in dams with state space model. So what is the alkali-aggregate reaction? It is a chemical reaction where the concrete will react with the ambient humidity. This reaction will lead to the creation of silica gel. This silica gel will fill up the concrete blocks and lead it to its expansion. This expansion will lead to some cracks inside of structures, and it can be critical for the integrity of our structures, such as the concrete dams that we have in Quebec. There have been many studies and models that have been developed to better understand this alkali-aggregate reaction. Among those models, one of the most famous one is the Larry's models. She has studied different blocks of concrete in laboratory conditions, and she had found one expression of the expansions according to time and one temperature. This formulation depends on three parameters that are the latency time τ(L), the characteristic time τC, and the ultimate expansion epsilon infinity. We can see on the left a plot of this formulation, and this formulation can be divided in four phases, where the first phase is when our concrete blocks will react with the ambient humidity and create silica gel. This silica gel will fill up the pores of our concrete blocks and will apply some pressure on these concrete blocks, which will lead to its expansion, as we can see in these second phases. And those two first phases will be characterized by the parameters of the latency time τ(L). At some point, the pressure will be high enough to create some micro cracking inside our concrete blocks, which will create a new space in which the silica gel can fit in. This will have an effect of slowing down the expansion rate, the expansion velocity of the concrete blocks, as we can see on the third phases. And this third phase is characterized by the characteristic times τC. And at some point, the expansion will be not possible anymore. We will hit this limit of the ultimate expansion, either when the reactants are not sufficient anymore, or because the condition don't allow the concrete blocks to keep growing. Now I want to put this model in context with the real data that we have studied. The monitoring data of the dams that we have studied usually start at the 1990s, and those dams are usually constructed or usually built around the 1930s, the 1940s. So if we want to put those data on a plot of the expansions over the time, we will put those data on the right relative to the time axis. So those data will represent unscented phases of the alkali-aggregate reactions. So if we want to adjust a Larry's model on those data, what will happen is that we will only adjust the numerator terms of the Larry's models. Why? Because it's when t becomes bigger, only the numerator term of the Larry's model will be dominant. So only with those advanced phase data, we will only be able to identify the two parameters of the characteristic time and the ultimate expansions, and the parameters of the latency time will not be able to be identified by those data that we have here. But one can say that if we know the value of the characteristic time and the expansion and the ultimate expansion, we can retrieve one value for our latency time, as we have done here on the left, where we have found latency time value of 4 and have been able to adjust one Larry's model thanks to that. But one need to notice that we can have multiple different value of these latency times parameters to adjust different Larvis model, and those different models will have the same shape and will be well adjusted to those, and will be similarly adjusted to those advanced phases data that we have here. So what does that mean? It means that we have not an unicity of the value of the latency time. If we want to have this unicity, we needed to have some data that will show that will correspond to the beginning of the reaction. So we will restrict the study of this reaction, of the Alkali-Aggregate reaction, only to a term that will looks like the numerator of the Larvis model. And in this numerator, we only have one exponential function. So that's why we are motivated to develop an analytical exponential component to monitor the Alkali-Aggregate reaction in dams. Now, if we want to study the displacement of the dams, we need to take in account additional complexities, such as other effects that can affect the displacement of the dam. For example, other than the Alkali-Aggregate reaction, we can have the variation of the season that happens in real life. Those season changing will cause the variation of the temperature. The variation of the temperature will cause the compression of the expansion of our materials, which will lead to seasonal effect about the displacement of our dams. Another complexity that we will have is that we will use some theoretical models to predict the displacement of our dams, and those theoretical models are not able to take in account the whole complexity that we have in real life. So we will have some discrepancies between the predicted displacement made by those theoretical models and the real displacement value of our dams. So we need to quantify these discrepancies, by quantifying what we call model errors. Another thing is that we will use sensors to retrieve the value of the displacement of the dams, and by doing so, the sensors are not able to retrieve at 100 precision the value of the displacement of dams. We will have discrepancies between these captured values by the sensors and the real displacement of the dams. And we will need to quantify these discrepancies as well by taking into account what we will call observation errors. Now, knowing that, we will want to use the state space model and the Kalman filter because they offer an ideal framework to analyze those type of systems where we will have a lot of different effects that are combined, and by accounting those model errors and those observation errors. Now, to understand how state space model works, I propose this simple illustration where we will launch characters through a cannon and we will try to predict its trajectory over time. For that, we will know the initial position, velocity, and acceleration of character. If we put in equation this setup, we will have the following variables, which are the position, the velocity, and the acceleration. We will use the theoretical kinetics model, which say that if we know the position, velocity, and acceleration at one time t, we can predict those variables at the time t plus 1. Each time that we will do a prediction, we will come also to observe the position of a character with either our eyes or a sensor. Now, since we are using a theoretical model, the prediction made by a theoretical model might have some discrepancies compared to the true value of the trajectory of our character. We need to take into account those discrepancies. And another thing is, if we come to observe with our eyes or with a sensor, we might not be able to point precisely on the position of our character. We need to also take into account those discrepancies, as we said before. So for that, we will introduce two variables, W and V, which will respectively take in account the model errors and the observation that we have discussed before. Now, if we use these kinetics models and we start with our knowledge about the initial position, initial velocity, and initial acceleration, if we apply the kinetics model on these initial states, we can do a first prediction and get these predicted states, and we can also come to observe our character to get the observations at the exact time step with the prediction state that we have done. Now, this prediction state is by using the kinetics theoretic model. So we have some model errors term in this predicted state, and in this observation model we have those observation errors. So we will want to do a combination of information between our observation model and our our prediction models, and by doing so we'll get a new state named an updated states where we will combine the whole information that we have on the observation model and the prediction model. So this updated state will be the state with the most information that we have of our character position on this time step. So we will use this updated state to do a new prediction, and we will observe again the position of our character. We combine again this prediction model with this observation model to get the update step, which is the state with the most information that we have at this time step. And we can repeat the same actions, doing a prediction and observation, combining the information to get the update state, and again prediction, observations, update step, and then we can have the full trajectory of our character. A simple notice is also that not that I have showed this simple illustration by using point values, but in reality we will not only use point values. In reality we don't have deterministic stats. We will have more knowledge about the trajectory of our characters. What does this imply? It implies that we will more know a mean value for position and standard deviation, and this will be represented more by a point and an area around the point, and the true value of the trajectory will be inside the point value and its area. Now we have some shortcomings with the Kalman filter, especially if we want to use it with the exponential component. One of the things is if we use the transition equation of the Kalman filter. This transition equation is for linear system. In other words, we need to be able to express the variables at the time t as a linear combinations of the variables at t minus 1. But this is not doable. We don't have a matrix A which will be able to have this strict equality between the exponential of variables at the time t with a linear combination of those variables at the t minus 1. We cannot express a linear combination of variables at t minus 1 to be equal to this value of exponential of those variables at the time t. There are some extensions of the Kalman filter that can help to do some non-linearities studies, such as the extended Kalman filter, which propose to replace the matrix A by a Jacobian, but by doing so we do a linearization of the first order, and this can lead to the divergence of our Kalman filter. Another way is to use the unscented Kalman filter, which will use sampling through some sigma points, but by doing samplings what we will lose is the fully analytical formulation of the standard Kalman filter. So now we have those following goals for our study. We want to have a fully analytical formulation for the exponential components. We will want to adapt the algorithm of the Kalman smoother, of the filter, of the Kalman filter and the Kalman smoother to use this analytical formulation that we will have for the exponential component. And we will want to verify our methodology on synthetic data, where we will have the full control on the context of those synthetic data. And one last thing, we will want to validate our methodology, validate the performance of this exponential component and on the whole methodology on real data. So now what we will do is we will construct step by step an analytical formulation for our exponential components. For that, we will start with a simple formulation where we will have a decaying exponential parameterized by a constant time. What this constant time will do, we can see on this right plot where we have plotted the exponential component over the time with a different value of the constant time. And as we can see, as the constant time increases in its value, the curvature of exponential are less and less steeper. So this constant time tau is here to control the curvature of our exponential, and it allows us to study different shape of exponential. But now if we keep this simple formulation, we have a problem where we will remain in the domain of 0, 1 as the displacement value, or in reality the displacement caused by the reaction of Alkali-Aggregate reactions will not remain supposedly on a domain of 0, 1. It can be a higher value. So for that, what we will do is just adding an amplitude factor A to our formulations. And by example, if we take A equal to 10, we are now not in the domain of 0, 1, but in the domain of 0, 10. But there is another problem with this formulation, is that our exponential component starting with an initial value. And why does this cause a problem? Is because if we combine the exponential component with other components of the SSM, such as a local level, this local level component can be biased and think that this initial value of the exponential component is its own initial value, and then will be biased by this value. So what we want to do is that our exponential components start at a 0 value at the initial time step, and for that we will only add a unit shift at this exponential, and therefore we have a 0 value at the initial time step for exponential, and the shape and the amplitude of exponential remain the same as we have previously determined with the two formulations. Another thing is in the last slide, what I have presented to you is a deterministic formulation for the exponential, but in why deterministic is because the parameters of the amplitude factor A and the time constant tau was known, so that's why I was able to come and plot those exponential components. But in reality, for those exponential, for the Alkali-Aggregate reaction, those parameters of A and tau are unknown. They need to be learned. And for that, we need to express them as random Gaussian variables. So we declare those variables, XA, which will be the factor amplitude, which will be a direct image of the factor amplitude, the deterministic factor amplitude that we have before. And to understand the link between the variable of XLTE, X latent time, and XLR, X latent rate, and our time constant tau, we need to discuss more about the notion of time that we will use for our SSM. For our SSM, we have arbitrarily chosen to come and discretize the time t and not using an absolute time t. So by doing so, we're discretizing the time into time step, which will be a multiple of 1 over tau, and the increment of 2 time step will then be the value of 1 over tau. So if we represent this discretization with the variable xLTE and xLR, what will happen is that xLTE LTI will be the direct image of the multiple of the multiple of 1 over tau, and XRR will be the value of one increment, which is the value of 1 over tau. So if we come and write down those variables as random, as what we call latent variables, we will have the following assumption about the dynamics of those variables. We expect that for the reaction of Alkali-Aggregate reaction, the amplitude will remain the same over the time step. The latent time will be at the time t plus 1 will be the addition between the latent time at the time t and the latent rate at the time t. So the addition of those quantity at a previous time step, and the latent rate, which is the reaction of which is the velocity of the reaction, will remain the same during the Alkali-Aggregate reaction in the times. Now we will want to use those latent variables with nonlinear operations such as the exponential or the multiplication to retrieve the exponential component that we have formulated before. And arbitrarily, we will decompose this component into two auxiliary components that are nonlinear, that are ZE and ZP. ZE will be the unitary exponential. Meanwhile, ZP will be the multiplication between our amplitude factor with the exponential, with the unit exponential. If we come to write down the hidden state vector and the moment associated, what we will need to notice is that if we use the standard Kalman filter on this formulation of the exponential component, only our latent variable will be well propagated by the Kalman filter. Those moments in black will be well propagated by the Kalman filter because they are following a linear dynamism. Meanwhile, our state in red and a moment in red, which are going through some nonlinear operation, will not be well propagated by the standard Kalman filter. So for that, what we want to do is to use closed form solution to compute the exact moment about our operation of the exponential and the multiplication. So here we can find the closed form solution that we use for the exponential operations. They are coming from the log normal distribution and the linearization for the term of the covariance with our exponential. For the multiplication, we have those closed form solution. They are coming from the Gaussian multiplicative approximation developed by Descartes and Goulet. So if we use those closed form solution on the Kalman filter, we will have this adapted algorithm. I propose to go step by step to understand what have changed between the standard Kalman filter and this adapted Kalman filter. So if we go with our variables and we go through the standard Kalman filter prediction step, what will happen is, since this prediction step are developed only for linear system, only our latent variables will be well propagated. Only the moment of the latent variable will be well predicted by this standard Kalman filter prediction step. We will need to apply those closed form solution on those propagated moments to obtain the nonlinear moment of ZE and ZP. And by doing so, we will have the exact moment of the exact predicted moment for both our latent variables and our nonlinear variables ZE and ZP. And therefore, we can apply the standard update step of the Kalman filter. Once again, it was developed for linear systems, so only our latent variables will be well updated through this update step. And we will need to apply again the closed form solution on those updated latent state to get the moment of our to get the updated moment of our nonlinear variable ZE and ZP. We are adapting the Kalman smoother algorithm also. At two places, we will apply the cross-form solutions. On the first place is when we will calculate the cross covariance, because these calculations imply the transition matrix A. This transition matrix A is only here to represent the linear combination that we have for our system. So it does not represent for the nonlinear variables that we have, and that's why we need to apply those closed form solution to get the cross covariance of our with our nonlinear variables. Another thing is if we apply the alter smoothing step on the usual Kalman smoother, this smoothing step is only developed for linear systems once again. So only our latent variable will be well smoothed by this step. And we need so to apply again the closed form solution on those well smoothed latent variables to get the smooth value for non-linear variables ZE and ZP. I want now to share some results. First, verification on the methodology that we have. For that, we have this first synthetic cases where we have set up values for the parameters of the exponential, which are x latent time, the value that we will go through the exponential operation, x latent rate, which is the parameters that control the curvature of the exponential, and xa, the parameter that will control the amplitude of the exponential, the value for which the exponential will converge to. We have the value of those parameters represented in those black dash line on the three sub figure that we have here on the right. And with those value of parameters, what we will do is we will construct an exponential, decaying exponential behavior, in which we will have, we will add at each time step some noises in order to have those synthetic data represented by those red dots. And those data, we will split them into two sets, one training set and one test set. In the training set, we will use our adapted Kalman filter to retrieve the parameters of the exponential. And with those parameters, what we will do in the test set is some prediction to see if those predictions will fit or not the data that we have on this test set. So what we will do to initialize the Kalman filter, we can see on this example, we will just take a shifted value of a value that will be shifted from the two parameters, and we will set the variances in sort of that this shifted value with one standard deviation that we set will contains the true parameters. So if we do so, we can see that the Kalman filter is able to find the parameter for x error. It will start by this value and it will slowly over time converge to the true value of the parameters. Same thing for the parameter of xa. We can see that the Kalman filter is trying to find the correct parameters. It will oscillate to run these true parameters, and at the end will converge to these parameters. We can see that the decaying exponential behavior is also well found by our Kalman filter, as we can see on this by this cyan line, and the prediction made by our Kalman filter of the prediction that we made with the parameters that we found with the Kalman filter fits the data that we have on this test set. We can come and complexify a bit this scenario by adding other effects such as seasonality terms, and we conclude on the same thing as the last result, as x error is converging to the true parameters. xa have also the same behavior and will converge to the true parameters, and the prediction that we made are fitting the test data. Same thing if we come here and add a local level component here. We can also try the Kalman-Swiffer algorithm that we have adapted, and as we can see, this Kalman-Swiffer adapted is smoothing well our value as the estimation of the two parameters XLR and XR are right at the beginning on the true parameter value. And even the decaying exponential behavior is the estimation is directly on this black dashed line. Now we want to do another synthetic study to come and study the sensitivity about the initializations of our exponential component with the adapted Kalman filter. Why we want to do that? It's because on the last case, what we have do is we have taken the value of the parameters to set the priors that we will set for the Kalman filter. But in reality, we will not have access to those value of parameters. So we cannot set the priors thanks to those parameters. So now we will come to the reverse. We will say that we know the priors that we will set the Kalman filter with. So the mean value of the parameters and the standard deviation of the parameters. And what we will do is we will draw some samples from a normal distribution with those priors knowledge that we have. So by sampling those parameters, we can come and synthesize some exponential behavior, as we can see here on those red red plot that we have here. And we will do 3 different scenarios where we will have different level of coefficient of variations. And we will change the value of those coefficient of variation by playing around the value of the standard deviation. So in this case, what we will do to summarize is we will draw parameters from a normal distribution for both of our parameters A and B that are the amplitude of the exponential and the constant time for our exponential here. And as we will increase the coefficient of variation, we will now draw those parameters from another normal distribution which are wider. That means that those parameters can take value in a wider range of possible values. And that's why the exponential behavior is taking a wider range here than the case where we have 12.5% of coefficient variation. We can even set an extreme case where we will have high uncertainty of 50% of coefficient of variations. Now for each scenario, what we will plot is those 2 figures. And for those plots, we will have on the y-axis the estimation made by the Kalman filter, and the x-axis the true value of the parameters. And if the estimation made by the Kalman filter are good for those parameters, we should see that the dots that we have here should be aligned with the red dashed line that we have on the diagonal. So for the case with low uncertainty as 12.5% of coefficient of variation, we can see that our Kalman filter have retrieved good estimation for both the X latent rate and XA. Now, if we come to the medium scenario of uncertainty of 25% of coefficient of variation, we can see in the majority of scenario of cases, the Kalman filter converge to a good estimation of the parameters, but there are some outliers. But if we come and see the prediction made on those outliers, if we come to focus on those 2 outliers to see the prediction, we can see that the prediction made on the test set are not fitting the data that we have here. So what we can do is just to refuse the parameters that our Kalman filter have found and launch new study with other prior knowledge to make our Kalman filter converge to the true parameters. Now, if we come to the extreme case of high uncertainty of 50% of coefficient of variation, we can see that we have plenty more of outliers. So we recommend highly to not use our exponential component with such an extreme case of high uncertainty, but rather to come and try to get a more informative prior knowledge, either by asking some expert advice to set up the parameters of the system that the user will be studying. Or as in our case, what we have done is we have used an automatic initiation algorithm to use which will use the training set to get more informative prior knowledge for our time series. But even though we have a lot of better case of estimation thanks to this automatic initiation algorithm, there is still outliers that are remaining, and if we come to see the prediction made on those outlier cases, now we are not able to distinguish if it is good or bad fittings. We cannot say that it's a bad fitting on this test set. So we cannot refuse the parameter found by the Kalman filter here, simply by doing a visual inspection on the prediction made on the test set. But we need to discuss about this result, because here the exponential behavior that we have here are very marginal for both of those cases, and that's why we think that the Kalman filter have not found the good parameters for those cases. It's because the exponential behavior are way too vanished and cannot be well studied by the Kalman filter. Now we want to test the performance of our exponential component on the real data. For that, we propose this first procedure where we will compare the exponential component with other components that we use in SSM, especially the acceleration component. For that, we will use this real data that we will split into three sets. One set which will be the training set, where we train again the Kalman filter, the adapted Kalman filter, to retrieve the parameters of the model that we will be studying, and a test set where we will make a prediction to see if the parameters found allow us to have a good prediction that are fitting those test data. And we'll do more prediction on this forecast to see the long-term behavior of the model that we are studying. So if we use an acceleration model that will retrieve its parameters on this training set, if we do some prediction on the test set, we can see that the prediction made are fitting the test data that we have. But if we keep doing prediction on this forecast, we can see that the long-term behavior is going to the contrary direction compared to the training and test set. And this is not the type of behavior that we are expecting for an alkali-aggregate reaction in dams. But instead, if we use an exponential component that we come to train and retrieve the value of the parameters, that we do prediction with those parameters, those predictions are fitting the test data that we have here. And if we do the forecast, now we have this behavior where the exponential, where the tendency will keep going on the same direction, and the speed rate of the tendency will becomes slower and slower, and tend to a certain value, which is the behavior that we expect for dams that are affected by the alkali-aggregate reactions. Now we want to study a last case of real data where we'll have a regime switch. So in this data, we can see that we have two regimes. That's because we have come to do an intervention on the structures. So what we want to do with this data is once again to split it into a training set where we will try to retrieve the parameters of our exponential, and to make predictions on this test set to see if the parameters found make us able to make predictions that are fitting the test set or not. But the procedure that we will do on the training will change a bit, because since we have two regimes, what we will do is we will train the exponential component on this first regime. We will get first values of parameters for the exponential for this first regime. And what we will do is we will inject some variances to those parameters to see if after these interventions our exponential component is able or not to adapt its own value to get this new regime and make good prediction on this test set. So if we do this study, we can see that after the time of intervention where we have added the variance onto the exponential behavior, that the exponential have indeed adapted itself to the new regime, and that the prediction that we make on this test set are fitting the test data that we have here. So our exponential component can help to quantify the regime change after an intervention on the structure. So now we can conclude the study that we have made. We can say that we have found an analytical formulation for our exponential component, which will retrieve the exact moment for the nonlinear operation that we have in these components, that we have integrated those solutions into the Kalman filter algorithm and the Kalman smoother algorithm, that we have verified this methodology on synthetic cases where we have concluded that we need to remain within a range of 25% of coefficient of variation to make the Kalman filter works. And we have validated our performance on real data where we have shown that the exponential model and those type of real data are working better than the acceleration model. And we have shown that our exponential component with this adapted methodology can help in quantifying regime switch after an intervention on the structure. So we have developed at the end a tool that can help to analyze analytically to help the monitoring of infrastructure affected by exponential deterioration, such as the reaction of alkali-aggregates. Now there is some shortcomings about our study. Firstly, it is about the initialization. We haven't found yet a robust way to initialize our Kalman filter or adapted Kalman filter to always have this convergence of towards the true value of the exponential. And another thing is that we have made the assumption of stationarity. In the SSM words, we will say that the Q matrix is equal to 0. And in other words, we can say that what we have made as assumption is that the parameters of the latent rate and the amplitude factor are remaining the same over the time, which cannot be true for other exponential deterioration. So we want to give some research perspective, some research future work to come and improve our methodology. First thing is about the stationarity. What we can see is that our variables of latent time and latent rate are following local trend model, and our variable of the amplitude is following local level model. And we know that those for those local level and local trends model, there is already some Q matrices that are defined in the literature of a state space model that can help, that can come and take in account those non-stationarity. So what we can do is to come to adapt again the Kalman filter, and here instead of only doing a prediction step of the usual Kalman filter, we'll also add a Q exponential matrix. We will add a non-stationarity to our latent variables. So those latent variables will be well predicted and non-stationary. And as we will use the closed form solution on those latent variables that are non-stationary, what we think is that ZE and ZP will directly be non-stationary thanks to that. Now another thing is that we will try to use the logarithm function. So what we do actually is we use this x LTI value. We go through the exponential to get ZE. ZE we go through a multiplication to get ZP. ZP we will compare it to the observation. We will do the Kalman adapt step, and we will come to update linearly this XLTI value. And by doing so, we are doing two linear approximation and two non-linear operation, which are the multiplication and the exponential. So instead of doing to linear approximation, what we propose is just to come and update linearly ZE from ZP. So we'll only have one linear approximation on the multiplication operation. And instead of doing a linear update on the exponential, what we do is we go through the inverse exact function that are the logarithm for the exponential. And by doing so, we think that the value of the updated XLTE will be more precise.